Let's consider the following circuit where we're going to have a current source providing some DC current IS. And then over here, we're going to have some resistor R, some inductor L, and some capacitor C, or our resistor, capacitor, and inductor are all connected in parallel. And I'm going to put a switch here in the middle. And what's going to happen is the switch is going to change from closed at A to closed at B at time T is equal to 0. Okay. So for time T is less than 0 minus, meaning before our switch change states, our circuit is at DC steady state. And so we can represent it as follows. Our current source IS is going to be the same. Since our switch is closed at A, our resistor is going to be directly connected in parallel. So we're going to have our resistor R. Our inductor L will be connected directly in parallel, but because we are at DC steady state, we're going to represent our inductor by its DC steady state equivalent, which is simply a short circuit. And our capacitor C is going to be replaced by its DC steady state equivalent, which is simply an open circuit. Okay. I'm going to define a few things here on both of our diagrams. So let's do these in blue. Okay. So let's call this my resistor current IR as a function of time. This is my inductor current IL as a function of time. This is my capacitor current IC as a function of time. And this is my voltage V as a function of time. This voltage V as a function of time represents the capacitor voltage, the inductor voltage, and the resistor voltage, since all three elements are connected in parallel. All right. So at T is equal to, or excuse me, for T less than 0 minus, we're going to have some resistor current IR at 0 minus. We're going to have some inductor current IL at 0 minus, some capacitor current IC at 0 minus, and some voltage V at 0 minus. And by inspection here, we can see that our inductor current IL of 0 minus is equal to IS. And by inspection, we can see that V of 0 minus is equal to 0 volts. We could also get values for IR at 0 minus and IC at 0 minus, but I'm bringing your attention to the inductor current and the capacitor voltage, because I want to point out here that since our inductor current is non-zero, that means that our inductor has some stored amount of energy. Recall from circuits 1 that the energy stored by an inductor, WL, is given by 1/2 L times IL squared. Since our inductor current is non-zero, we have energy stored in our inductor. For a capacitor, the energy stored by a capacitor is given by 1/2 C VC squared. Since our capacitor voltage is 0 in this case, we don't actually have any energy stored in our capacitor. All right. So For time less than 0 minus, we have some amount of energy that is stored in our inductor, depending on the value of L and the value of IS. For t greater than 0 minus, or for t greater than or equal to 0 plus, now our circuit is going to look like this. IS will be shorted out as the switch is closed at B. And then over here on the right-hand side, we are going to have our resistor, our inductor, and our capacitor. And we will have some resistor current IR of t, some inductor current IL of t, and some capacitor current IC of t, as well as a voltage V of t. Now, after the switch has changed states, what's going to happen is that our inductor, L, will start distributing its stored energy to the capacitor and the resistor, okay? So our goal today is to figure out the mathematical relationships behind that transfer of energy and how they relate to the quantities IR of t, IL of t, V of t, and IC of t that we have defined, okay? So how we're going to do that is we are going to write a KVL equation at the top right-hand node, okay? So I'm going to circle the node that I'm interested in right here. So we're writing a KVL equation. And I'm going to consider currents that are leaving the red node to be positive, such that I have IR of t plus IL of t plus IC of t is equal to 0. What I'm going to do now is I'm going to express all of my currents in terms of that voltage V, right? So for my resistor, the current flowing through a resistor using Ohm's law is simply V of t divided by R. The current flowing through an inductor in terms of the voltage drop across the inductor is given by 1 over L times the integral from t naught to some later point in time t, V of t prime dt prime plus IL at t naught, and the current flowing through an a capacitor in terms of the capacitor voltage is simply C dV by dt. I'll set this equal to 0. Okay. So this equation, I'm going to put a box around it. Is an integro differential equation because it has both integral and derivative based relationships in it. we are going to make this integral differential equation a little bit easier to handle by simply taking the derivative of both sides of this expression. Okay. So if I take the derivative with respect to time of both sides of this expression, what I'm going to have is 1 over r times the derivative of v with respect to t plus 1 over L times v of time, right? Because when we take the derivative of an integral, we're canceling out the calculus effectively. When I take the derivative of that constant term, IL at t naught, that's going to be 0. And now I'm going to take the derivative of c dv by dt, which is going to give me c dv squared by dt squared is equal to 0. And now what I'm going to do is just algebraically rearrange this slightly, such that my second derivative term does not have a coefficient, okay? Or the coefficient of my second derivative term is 1, I guess would be a way to do it, okay? So I'm simply going to divide everything through by a factor of c. In doing so, I have the relationship the second derivative of voltage plus 1 over RC times the first derivative of our voltage plus 1 over LC times the effectively 0th derivative of our voltage is equal to 0. And this is the characteristic second order differential equation which describes our system. This is actually the second order differential equation that describes any parallel RLC network. Okay. So our goal is to solve this second order differential equation. And we are going to solve this second order differential equation using our prior circuit experience. So when we had a first order differential equation for a RL circuit or an RC circuit, we observed that our solution was of the form, so in this case, it's going to be a voltage signal. V of t was equal to AE to the ST, where S, the eigenvalue of the system, was dependent on the circuit parameters, that the values of R and L or R and C, and A was determined by the initial conditions of the system. Okay. So we're going to reuse this guess, and we're going to see what happens. All right. So if I substitute this guess value of V of t is equal to A to times E to the ST into my characteristic second order differential equation, what I'm going to get is S squared AE to the ST plus 1 over RC times S AE to the ST plus 1 over LC times AE to the ST is equal to 0. And I'm going to very slightly algebraically manipulate this, okay? So I have a common factor of A, so I'm going to move that outside, I have an S squared plus 1 over RC times S plus 1 over LC. And then this is all multiplied by e to the st. And I'm going to set this equal to 0. This bit right here is my characteristic polynomial. And what it lets me do is solve for the different values of S that will make this equation true. Now, this characteristic polynomial is a second order or quadratic equation. And hopefully at this point in our engineering careers, we know very easily how to solve quadratic equations, okay? So since it's a quadratic equation, it should have two solutions. We'll call our first solution S1, where S1 is going to be negative b, where in this case, b is the coefficient on the s to the first power term. So that's going to be, like, let me give myself a little bit more space here. So we're going to have negative 1 over RC plus the square root of 1 over RC squared minus 4 times a, where a is the coefficient on the s squared term, simply 1, times c, where c is our constant term. So this is going to be 4 times 1 over LC and this is all divided by a factor of 2, 2a, right? Just using our good old quadratic equation. And what I'm going to do now is simply move this factor of 2 from the denominator into the numerator so that this equation isn't quite as bulky, okay? And so what that's going to look like is negative 1 over twice RC plus the square root of 1 over twice RC squared minus the square root of 1 over LC quantity squared. S2 is going to be the exact same thing, except we're going to have a negative sign in the middle. Okay. So negative 1 over twice RC minus the square root of 1 over twice RC squared minus square root of 1 over LC squared. And then all of this goes under the square root sign. All right, so in electrical engineering, we give this 1 over 2 RC a special name, okay? We're going to define alpha to be 1 over 2 RC, where alpha is known as the Neper frequency. Okay. The Neper frequency characterizes how our exponential decays. So it is very similar to our interpretation of a time constant for a first order RL or RC circuit. Okay. The units of the Neper frequency are Nepers, a dimensionless quantity per second. The square root of 1 over LC also has a special name, in electrical engineering. This is going to be our resonant frequency. The resonant frequency has multiple interpretations depending on what kind of system that we are looking at. If we were looking at a steady state sinusoidal system, our resonant frequency would represent the frequency at which the impedance of our network was purely real. For this type of system, what the resonant frequency represents is more akin to the frequency at which oscillations will be at their strongest value, okay? A resonant frequency has units of radians per second, okay? So if we use alpha and omega naught, we can rewrite our expressions for S1 and S2. So we could say that S1 is negative alpha plus the square root of alpha squared minus omega naught squared. And we could say that S2 is negative alpha minus the square root of alpha squared minus omega naught squared. Okay. So what we will find, circling back around to our original equation, is that for this second order system, our voltage V of t will be of the form A1 e to the S1t plus A2 e to the S2t, okay? So since our guess gave us two solutions for S, we have to have the sum of the guess values effectively, okay? We're able to do this because of the linear properties of circuits. Effectively, this is nothing more than the superposition principle. If our first guess was a solution and the second guess is a solution, then the sum of the guesses has to be a solution as well, okay? So this is our most general form of our solution, where S1 and S2 are given by the equations above, and A1 and A2 are solved for by looking at the initial conditions on the system. Specifically, we would be looking at, so let me write this down here. S1 and S2 equations above, A1 and A2 are determined by the initial conditions on V of 0 plus and the derivative of V evaluated t is equal to 0 plus. And we'll get into that in more detail in a minute when we actually start analyzing things. But before we do that, we actually need to consider multiple cases, okay? So let's look at case number 1. So in case number 1, alpha is greater than omega naught. Okay. We call this, actually, let's talk about the different consequences of this, okay? So if we scroll back up here and we look at our equations for S1 and S2. When alpha is greater than omega naught, then the portion of S1 that's underneath the square root sign is real, right? So we're going to find that S1 and S2 are negative so we're going to see that our response is simply the sum of decaying exponential signals, okay? We call this the overdamped case. And in the overdamped case, I'm just going to call this y of t. So generically, a signal in an overdamped system, this could be a voltage signal or a current signal, will be of the form A1 e to the S1t plus A2 e to the S2t, which is literally what we just derived, okay? Now let's consider case number 2. What if alpha were exactly equal to omega naught? Let's scroll up here. If alpha were equal to omega naught, S1 would be negative alpha and S2 would also be negative alpha. So effectively, when alpha is equal to omega naught, we have repeated eigenvalues or repeated natural frequencies for our system. The problem with this is, in our generic equation, we have two initial conditions that we need to take into consideration, one based on the value of V at t is equal to 0, and one based on the value of the derivative of V at t is equal to 0. Another way to think about it is we have two energy storage elements, so we should be having two initial conditions on our system. And if we have a single repeated root, our guess equation can't handle that. So I'm going to write something down here. So S1 is equal to S2. So we have repeated roots of our polynomial. And then this next bit, you don't actually need to write down because I'm going to erase it. I just want to explain what's happening, okay? So if we looked at our response equation here, y of t, we would have A1 e to the minus alpha t plus A2 e to the minus alpha t. We could just simply add those together. Our second initial condition doesn't do anything. So to correct that, what we do is we have, actually I should have left that alone. A1 t e to the negative alpha t plus A2 e to the minus alpha t. So when S1 is equal to S2, we have to slightly modify our response equation to account for the fact that we have a repeated root of our characteristic polynomial. And this particular condition we call critical damping. And finally, we will have case number 3. In case number 3, alpha is less than omega naught. So bear with me while I scroll back up here. What happens to our equations for S1 and S2 when alpha is less than omega naught? Well, the bit under the square root sign becomes negative, which means we have negative alpha plus some imaginary number. And S2 is negative alpha minus that same imaginary number. So effectively, S1 and S2 are now complex numbers that are complex conjugates of each other. So S1 and S2 are complex conjugates. And our response equation, in order to handle these complex conjugates, so we could simply write it out as, actually, let's put this, y of t is equal to a1 e to the negative alpha plus j, and let's call this omega, just omega for now, plus a2e to the negative alpha minus j omega. But in dealing with those complex frequencies, this would make the math incredibly hard, okay? Using Euler's identity, we can express this as B1 cosine, what we're going to call omega dt, plus B2 sine omega dt, and this whole expression multiplied by a factor of e to the negative alpha t. We call this an underdamped system. All right. So let's very briefly talk about the differences between an overdamped system, a critically damped system, and an underdamped system when it comes to their response curves. All right. So I am going to try to plot an arbitrary signal here. So here is T. Here is Y of T. This red signal will be representative of an overdamped signal. So overdamped signal, we're going to start at some initial value. And then gradually exponentially decay before settling to some final value. And it takes a long amount of time for us to settle. Critically damped circuit, the response is going to look almost identical, except that we're going to settle to our final value much quicker. Critical damping means we settle to our final value in the shortest amount of time possible, experiencing ringing. And finally, this in green, we're going to have our underdamped system. So what an underdamped system does is it's going to get down to this settling value very, very quickly, but then it's going to overshoot it. It's going to turn back around. Like so, and effectively do like this. So it's going to look like a sinusoid being multiplied by an exponential function, because that's exactly what it is. It's going to have sinusoidal oscillations that have an envelope of the exponential function that causes it to gradually decay to some fixed value. Okay. Now, before we analyze the circuit here, which is what we're going to do in just a moment, I want to make you aware of something. If you go to Moodle and you click on the link for today's class meeting, you will find a PDF version of this table. In this table, I have summarized the response equations for both parallel RLC circuits, which we have talked about today, and series RLC circuits, which we're going to be talking about on Friday. I have not only included our response equations for y of t, but I have also included the derivative-based equations that we're going to be using, as well as to find any other special parameters. For instance, I have our definition for S1 and S2, which we use in a overdamp system. I have our mathematical definition. So here's our definitions for S1 and S2. I also have our definition for omega D that popped up in our critically damped equation. In our underdamped equation. Our critically damped equation just uses alpha, which I've also got a definition for. So effectively, I've tried to create a table for you that is a one-stop shop for all of the different relationships that you might need to use for the next several class meetings. So I will be referring back to this guy over and over again as we actually work problems. All right, so let's work an example. So the circuit that I want us to look at is this guy, okay? Here we are going to have a 10-volt source. Connected to a 10 ohm resistor. We have a switch that is going to be closing at t is equal to 0. Connected to this switch is a 10 ohm resistor and another voltage source. Make this one a 20-volt source. And then we have an inductor. This will be a 2 Henry inductor. And over here we have a capacitor. And this will be a 10 millifarad capacitor. And I'm going to define some things here, okay? Here's my voltage V of t. Here is my capacitor current, IC of t. Here is my inductor current IL of t. There are multiple resistors here, okay? IR of t that we dealt with in our derivation isn't actually important to know what's happening for the behavior of the circuit now that we know how it generally behaves. But I want to determine, so let's call this voltage VR of t. And let's call this current IRT. Actually, I'm going to change the colors on these because these are going to be some of the last things that we determine. Okay, so let's make these purple. So our quantities in blue are really required of us to solve for to determine how our system is going to behave. The quantities that I've outlined here in purple might just be signals of interest that we need to figure out. But in order to determine the quantities in purple, we have to know at least some of the quantities in blue first, okay? So the first thing that I want to do here is to explain to you how and or why this circuit behaves like a parallel RLC circuit, which is what we're talking about today, okay? So in order to do that, our first step in analyzing a circuit like this, step number one, will be calculate alpha and omega naught and determine if the circuit is overdamped, critically damped, or underdamped. Now, because we have a parallel RLC circuit, we know that alpha is equal to 1 over twice RC. And we know that omega naught is equal to the square root of 1 over LC. Now, our problem here is that we have multiple resistors, okay? So I'm going to explain to you how to accommodate for that, okay? So what we're going to do is we are going to look at a dead network during the transient condition. So during the transient condition, means after our switch has changed states, okay? So for us, the transient condition is our switch is closed, okay? Dead network means that we have to turn off all of our independent sources. So we have to turn off our 10-volt source and turn off our 20-volt source. Turning off a voltage source means replacing it with a short circuit. So our dead network during the transient condition is going to look like a 10 ohm resistor in parallel with a 10 ohm resistor in parallel with a 2 Henry inductor in parallel with a 10 millifarad capacitor. So from this depiction, R EQ is simply 10 ohms in parallel with 10 ohms or 5 ohms. Right? So effectively, the energy storage elements, our 2 Henry inductor and our 10 millifarad capacitor, see an equivalent resistance of 5 ohms. Our resistor network sees an equivalent capacitance, C, of 10 millifarads and an equivalent inductance, L, of 2 Henrys. Using these results, alpha is 1 over twice RC becomes 1 over 2 times 5 times 10 to the minus, 10 times 10 to the minus 3, or 10 Nepers per second. And omega naught is the square root of 1 over LC So square root of 1 over 2 times 10 to the minus 3. 5 square root of 2. Which is the same as 7.071 radians per second. So since alpha is greater than omega naught, this is an overdamped circuit. And that means we are going to use our overdamped response equations, okay? But before we can use our overdamped response equations, we need to determine the conditions on the system, okay? So step number 2 will be to analyze the circuit at T is equal to 0 minus. Okay. At T is equal to 0 minus, we are at DC steady state conditions. So let me write that down. 0 minus So our switch is going to be opened up because it has not yet closed. Our inductor is going to look like a short circuit and our capacitor is going to look like an open circuit. So to me, that means we're going to have something like this. Here's our 10-volt source. Here is our 10 ohm resistor. Here's our second 10 ohm resistor. Here's our 20-volt source. Our inductor is going to look like a short. Our capacitor is going to look like an open circuit. Excuse me. And I'm going to define my parameters in blue, okay? So here is IL of 0 minus. This is an important quantity for us to know. Here is IC of 0 minus, another important quantity for us to know. Here is V of 0 minus, our third important quantity. Okay. So we are going to try to determine what these three quantities are. So it should be fairly obvious here. Our capacitor current, IC of 0 minus, has to be 0 amps because it represents the current that's flowing through an open circuit. Okay. Just as easily, we should be able to see that V of 0 minus has to be 0 volts because the voltage drop over our capacitor is the same as the voltage drop over our inductor, and our inductor is a short circuit. The voltage drop over a short circuit must be 0. So the only quantity that we're actually going to have to do any work for here is IL of 0 minus. Okay. So assuming that there's some amount of current leaving our positive polarity terminal of our 10-volt source, it will flow through the 10 ohm resistor, and then its path is through our inductor. And then back around like so. So this current that I've outlined in red here is our inductor current, and using just good old Ohm's law, we can find that our inductor current is 10 volts divided by 10 ohms is equal to 1 amp. Okay. So how did you feel about that circuit analysis? Anything difficult? Not particularly, just good old DC circuit analysis. So let's move on to step number 3. So in step number 3, we are going to analyze the circuit. At T is equal to 0 plus. We need to recall that VC of 0 minus and VC of 0 plus have to be the same thing because the voltage drop across a capacitor cannot change abruptly. And IL at 0 minus has to equal IL at 0 plus because the current through an inductor cannot change abruptly. So at T is equal to 0 plus, our circuit is going to look like this. Here's our 10-volt source. An ohm resistor. At T is equal to 0 plus, this is the instant that our switch is closed. So we're going to have a 10 ohm resistor in series with our 20-volt source. Now we have our inductor. Our inductor is carrying a constant current of 1 amp in the down direction. So I'm going to represent that by a 1 amp current source. And our capacitor is carrying a constant 0 volts. So I'm going to represent that with a short circuit. Now I'm going to identify my quantities of interest, again in blue. So this is our inductor current, IL at 0 plus. Here, I'll put the voltage here. It's still the same thing. Here's the voltage at 0 plus. And then here is our capacitor current at 0 plus. And we know that IL of 0 plus has to be 1 amp because that's what it was at t is equal to 0 minus. We know that V of 0 plus has to be 0 volts because again, that's what it was at 0 minus. So the only thing that could have changed is IC. So that begs the question, how do we determine IC here at 0 plus? Now, you may look at this and you may say, oh, well, it's going to be 1 amps because there's 1 amp current source in parallel with a short circuit. But I would argue, let's use some colors here, okay? So if we have any current leaving our 10-volt source, it's going to flow through this 10 ohm resistor. And then it has 3 different paths that it can take. It can take that path down through the 10 ohm resistor. It could take the path down through the 1 amp source, or it could take the short circuit, right? So there's going to be some contribution from the 10-volt source to our capacitor current as well. Similarly, there's going to be a contribution from the 20-volt source to our capacitor current, okay? So how I think we should approach this would be to use mesh analysis. Make sure that we have everything taken care of. So here is my mesh current. Let's call this I1. This is my mesh current I2. Here is my mesh current I3, where I3 is the capacitor current that I'm looking for, okay? So KVL at mesh 1, we have negative 10 volts plus 10 ohms times I1 plus 10 ohms times I1 minus I2 plus 20 volts is equal to 0. KVL at super mesh to 3. We're going to have negative 20 volts plus 10 ohms times I2 minus I1 is equal to 0. And then we're also going to have a current relationship that says I2 minus I3 is equal to 1 amp. Okay. So if we solve these three equations simultaneously, give me just a moment to do that. So let's see, in our first equation, our coefficient for I1 is 10 ohms plus 10 ohms. So that's 10 plus 10 is 20. Our coefficient for I2 is negative 10 ohms. Our coefficient for I3 is 0. And then our constant term is going to be 10 minus 20. So that's negative 10. And our second equation, our coefficient for I1 is negative 10. Our coefficient for I2 is positive 10. Our coefficient for I3 is 0. And our constant term is positive 20 volts. And then in our third equation, our coefficient for I1 is 0. Our coefficient for I2 is 1. Our coefficient for I3 is negative 1. And lastly, our constant term is 1 amp. And so I get I1 is 1 amp. I2 is 3 amps. And I3 is 2 amps. Since I3 and IC at 0 plus represent the same current, we can say then that IC at 0 plus is equal to 2 amps. Anything particularly difficult about that circuit analysis? Not really. All right. So the last thing that we're going to do here sorry, black. Step 4 is to analyze our circuit. I misspelled analyze, Barry Bradley. At t is equal to infinity. Okay. So at t is equal to infinity, circuit is again at DC steady state. Because the transient condition has long since died off. And so what that's going to look like is this. Here's our 10 volt source, 10 ohm resistor. Our switch remains closed. Our inductor is going to look like a short circuit. And our capacitor is going to look like an open circuit. Here is IL at infinity. Here's IC at infinity. Here is V at infinity. By inspection, we have IC at infinity is equal to 0 amps. V at infinity is equal to 0 volts. And the only thing that we need to actually do any analysis for then is IL at infinity. instead of going through the trouble of doing mesh analysis here, which we absolutely could do, instead I'm going to work this effectively using superposition, okay? So with the 10-volt source on and the 20-volt source off, we will have a contribution of 10 volts over 10 ohms to our inductor current IL. With the 20-volt source on and the 10-volt source off, we will have a contribution of 20 volts over 10 ohms to our current IL. And so this looks like 1 + 2 is equal to 3 amps. Does using superposition in this case make sense? Another way to do it would be effectively just doing Kirchhoff's current law at this node, where this current in plus this current in equals this current out, which is effectively what you get using superposition anyway. All right, so we are running a bit short on time right now. So what I suggest we do is we stop here and then we pick this problem up on Friday. So Friday, I had intended to work series RLC circuits, and we'll probably get to that towards the end. And then next Monday's class was just going to be working example problems. So things are going to shift by about half a class meeting or whatever. But all in all, it's not going to be particularly that much of a change that we're behind here. Okay. So on Friday, we'll pick this problem up. In fact, I'm going to make a point to save our work. And after we finish this problem and then talk about how we could simulate this circuit to verify our analytical results, we will move along to series RLC circuits.